So I'll be talking about recent work with Steve Scholar and Vlad Vikol on shock formation for the compressible Euler equations. So these are the equations that I'll consider. So I'll consider the non-isentropic equations. So we have the density, we have the velocity, and we have the entropy in this equation. Okay, and related to this, you can write your pressure law, and also you get a sound speed. So this is the speed at which small perturbations propagate. Okay, and for convenience, I'll introduce this alpha here, which is related to the pressure law. Okay, so and also I'll also consider the isentropic case, which is slightly easier, where we no longer have an equation for entropy. Okay, so before I go into the full 3D non-isentropic case, it's worth considering the 1D case. So in the 1D case, you end up with just this equation of the conservation of momentum and the conservation of mass. And what's particularly neat about the 1D case is you can rewrite these equations in terms of Riemann invariance. So if you add and subtract this 1 over alpha times the density to the power of alpha from the velocity, then you end up with just a transport equation, okay, where there's lambda 1 and lambda 2 wave speeds associated with the two Riemann invariants. This is nice because it means there's no loss of derivative, you just end up with a transport equation, okay? And so to give you an example, what happens in the 1D situation. So this is a video of the profile of the velocity, and you see that a shock will form at some point here. That stops, okay? And this is the kind of behavior we're looking for. So this is in 1D, and this is a slightly different data. So it shows that for certain data, you can have unstable. You can pick the data in a particular way that you have instability and say that two shocks could happen at once. But what we'll consider later is certain initial data where any sort of small perturbation will lead to the same shock profile. So we won't have this kind of behavior happen. I'll explain that more later in the lecture. So that's the same sort of video. So this is the type of shock that would look for in the case of 1D. This is known as the generic shock profile. And the reason this is called the generic shock profile is basically if you zoom in, if you give me any random 1D initial data, the solution will shock, and if you zoom in, it will look like this. Okay, and it's key that you're giving me any generic data. So there are particular ones that have different behavior, but if you take one of these unstable shocks, you can perturb it slightly and you end up with a shock in exactly this form. But if you start with a shock you start with initial data leading to a shock in this form and you perturb it a little bit, it will lead exactly to this type of shock. So this is a stable shock in the case of 1D, the 1D Euler equation, or the one. So this is in fact the 1D Burgers equation. The same thing happens for Euler. Okay, so yeah, so this is the case for. This is an example of the case for Euler. Okay, so it's the same. Looks exactly. If you zoom in here at where the shock happens, it looks exactly like the one we had before. Of course, away from the shock, everything's different. Okay, so I'll give some brief history. So in '64, Lax proved in the 1D case that singularities form, and it was key that he used these Riemann invariants that I had on the previous slide. He follows trajectories and you end up with a proof by contradiction. And this was extended by John, Leo, Kahneman, Maida, and Maida in the 1D case. In the 3D case, this was sort of, these singularities were proven in the case of 3D wave equations with quadratic nonlinearities. Sideris was the first to prove the breakdown of solutions of 2D and 3D solutions. And again, this was a proof by contradiction. So the key thing here is that something goes wrong, but you don't even know exactly what goes wrong. And I want to consider the situation where you know exactly what goes wrong. Okay, so this is just an example of, to give you an intuition of some of the advanced dynamics that can happen in Euler. So this was a numerical paper by Rami, a Reisman scholar, and here you have all sorts of things, all sorts of shocks, contact singularities, all sorts of things. So we won't prove all that, but one thing to note is that you see that there's actually these azimuthal shocks that happen, that go around. We'll prove a result related to azimuthal shocks as a sort of introductory result. So Christodoulou in 2007 showed for small data irrotational flow shocks form, and this was first done in the relativistic setting, and then in the non-relativistic setting with Miao. And the idea is to perturb a simple plane wave. So a plane wave causes a shock, and you want to perturb it in a non-trivial way in 2D and 3D, and so show the same sort of phenomena happens. What's quite remarkable in this type of result is that if you consider irrotational flow, then you do not have what's called vorticity waves. You only have sound waves, and because of that, the singularity takes a long time to develop, and so you start with some initial data, and it takes a very long time, and they can be able to control it up to this very long time, and then a shock occurs. So this will not be the case in the situation that we will consider, but it's an interesting phenomenon. So the issue with 1D plane waves is that, so say you wait until a shock occurs. If you make a small perturbation of this initial data, it's possible. So in this case, the shock occurs along a line. It's possible that a shock could occur, if you perturb a little bit, a shock could occur at a single point, or a shock would occur at multiple points, or anything in between. Okay, so it's an unstable behavior in this sense. And in general, if you perturb it, what will actually happen is it will shock at a single point. And this is what we'll be interested in, single point shocks, because they're the stable kind that you expect. You expect that it happens at a single point, but then it stretches, as you develop the shock, it will stretch out to a line. Okay. So this is just a brief overview of their methods. So they introduce the iconal function and introduce geometric coordinates in order to track the shock. They have long time existence because you have you're in the rotational setting with small data, and they show, in order to characterize the shock, in a shock they show that the distance between characteristics goes to 0, and they show no other type of singularity can occur. So it's not like the previous results where you just don't know what happens. You know what type of singularity occurs at the time, but you don't know some of the information which I'll discuss later. For example, you don't know that the initial singularity will happen at a single point, and so forth. And yeah, so this is a little note about the irrotational things that you can take into account. Some commutation with Gaussian boost in order to get long time existence. This is why you get this delayed singularity occurring. And to actually prove it, you use a Klein-Solomon inequality to prove that you have this delayed shock. Okay, so for the particular case, for this irrotational case, that Euler becomes a 2D quasi-linear wave equation for the velocity potential. So in particular, you only have sound waves interacting, no vorticity waves interact. And there was prior work by Alanak where they proved stability of a blow-up profile for 2D second order quasi-linear wave equations in 2D, and which is somewhat similar in spirit to our work, but it doesn't cover the Euler case. And I just want to point out in the last chapter of Christodoulou's book, he classifies what it means to be a generic shock, and that's although they do not prove that a generic shock occurs. Okay, so this work by Christodoulou was extended by Luke and Speck, where they were the first to establish shock formation for 2D Euler with non-trivial vorticity. And this followed Christodoulou's work, and they had to develop new methods to deal with the interaction between sound waves and vorticity waves. What we want to do is find an open set of initial data that yields a generic shock in 3D. And in 3D, you have additional problems because so in 2D, vorticity is transported, and in 3D, vorticity is stretched. And so new ideas are needed there. And we want to, in addition, we want to specify initial data where it leads to a specific shock profile, which we can prescribe exactly, and we know nothing else happens. So all these results before, you don't know anything about the initial singularity. You don't know if it occurs at a single point or a line or so forth. In this case, we know it given any small perturbation in some suitable smooth norm, you will always end up shocking at a single point. And you'll always have precise information like the Holder regularity of the solution at the time of singularity and such. And we will also consider the non-isentropic case. In this case, you have three types of waves interacting. You have sound waves, you have entropy waves, and vorticity waves. And as far as we're aware, it's the first sort of result that is able to handle these three types of waves. Okay, so what do I mean by a stable shock? So we want to specify some open set of initial data within a suitable topology. And we want to classify whether the singularity occurs at a single point, multiple points, a line, a surface. And we want to give the precise regularity of the solution. And we want to be able to compute the space-time location of the singularity, and it has to be stable in the sense that you make a small perturbation, suitable topology, and you get all the same characteristics occurring. And in fact, we have something stronger. We know asymptotically, if you zoom in on the singularity, exactly what it looks like. So it converges to a solution to 3D burgers. But so viewed in the right way, it converges exactly to a solution of 3D burgers, and so you have an exact description of this self-similar profile at the singularity. Okay, and this is the first result of its kind. Now, before I mention the full 3D result, I just want to mention this work that preceded it, which is on 2D shock formation with an azimuthal symmetry. And the thing I want to stress about this result is, if you're interested in any of these results, then this is the paper to read, because this is where we kind of develop the main techniques which are used to attack the harder problem. And so the principal ideas are all contained in this, although it's much harder and there's more ideas needed in the 3D case, the full 3D case. Some of the principal new ideas that are in this result. So it's 2D with symmetry, so it becomes a 1D problem. So we assume azimuthal symmetry, so the shock will occur in the angular direction, and you can see here a shock occurring. And what we actually do is we consider the free evolution of the solution, so you can kind of cut it off at a particular radius. It's not an exact radius because the surface moves, but it's something like that. Okay. And so what we prove in this paper is that if you rewrite these equations in terms of this azimuthal symmetry, then the symmetry is first preserved. Now you just have the equation in terms of the angle and the time. We write Riemann invariance in terms of this equation. And then if you write, these are the equations you end up with when you write things in terms of Riemann invariance. And what we want to do is that show that if you zoom in at the singularity, none of these other terms matter apart from these blue terms. So these blue terms, you see, if you just keep these blue terms, you end up with Berger's equation. And what we want to say is that if you zoom in on the singularity, that's all you see. You see Berger's equation. Okay, so what we show so this is what we show is that there's an open set of initial data in C4, which leads to a stable shock formation. So given that you start epsilon time before the shock, then with a slope of 1 over epsilon, then the solution occurs basically at t equals 0, modulo a lower order error, and that it's C1/3. You can compute the angle, and you can also show that you have non-trivial vorticity at blow up. Okay, so let me go on to the 3D case. So this is the 3D non-isentropic case. So these are the equations, and as I said, we have, we want to rewrite these equations in terms of the rescaled sound speed, and this gives us some nicer equations here. And the point is that the transport is of the same. Sorry, everything is of kind of the same order by taking the right power of alpha. Now we don't want to deal with the vorticity directly. It's much nicer to deal with the specific vorticity, where you take the vorticity and you divide by rho. And in the isentropic case, you just get this blue part equals 0. So it's just the typical equation you're used to in, say, the incompressible 3D case of 3D vorticity. You have transport and you have stretching. In the non-isentropic case, you have this additional baroclinic torque. Okay, and this is something which will, as you go to the singularity, this will go to infinity. Okay, so it's an additional difficulty to handle. So this is like a forcing which will go to infinity, yet the vorticity will remain bounded. Okay, so it will go to infinity, but in an integrable way, in the sense that you have to, I'll talk more about that later. Okay, you have to integrate this equation in the right way. Indeed, you have to integrate it along trajectories, and then you see that you can bound this contribution of this forcing. Okay, and one also thing to note about the non-isentropic case is you can start with irrotational data, and vorticity will be created from entropy. So this is something that doesn't happen in the isentropic case. And we can actually show initial data that starts as irrotational initial data and has non-trivial vorticity at the shock because of this vorticity creation. So this is the kind of results we can do. Okay, so the main idea, it sort of follows in the framework of this 2D case with azimuthal symmetry, although it's much more difficult. Okay, so the first idea is to rewrite space and time in terms of self-similar coordinates. And then we also have to rewrite the velocity and the sound speed and the entropy in terms of Riemann variables. And we want that one of these Riemann variables behaves exactly like 3D burgers. And so the stable generic shock that you have in 3D burgers also occurs for the Euler. That's the plan of attack. And so in particular, if you take let me see if I can move my video. Okay, so in particular, if you consider the 3D self-similar burgers equation, that is, I'll describe it shortly, how you get this self-similar equation. It's this. If you write the velocity in terms of this self-similar scaling, then you end up with this equation here, 3D burgers, and there's an exact solution to this equation. So there's an exact self-similar solution to 3D burgers. Okay, and this solution shocks at a single point, and this is stable with regards to perturbations. Okay, and so then yeah, so this is, once you have this self-similar solution, you set the velocity, the first component of velocity to be equal to this, and the other two components to be equal to 0. And this is an exact solution to 3D burgers. The important thing to note here is that this Hessian matrix is strictly positive definite, and this is what gives the stability of this shock. Okay, so this is what it looks like. You see a steepening, and you see a self-similar singularity here, occur in the middle. This is for 3D burgers. Okay, and for compressible Euler, this is a video. Okay, and you only really care about the behavior at the singularity, and it should be exactly like the previous video. And this actually continues a little bit past the shock, so it continues the shock. Okay, and this is a side view of the same video. And so a shock occurs, and then it continues a little bit past. Okay. We don't say anything about the continuation of the shock. We only say up to the time of the shock. Okay, so I might switch to my well, I don't have that much time, so I'll keep in the slides. Okay, what are the difficulties in dealing with the Euler equations as opposed to, say, the 1D Euler equations or 2D Euler equations for symmetry? It's much harder to isolate the burgers-like behavior in 3D because so much more can happen, okay? And so what you have to do in order to, so that it looks like, in order that you look like the 3D burgers equations, you have to introduce certain coordinates, and all these coordinates will be defined in terms of 10 dynamic constraints, which are related to the zeroth derivative of W, the first derivative, and the second derivative, which means that we will need 10 different constraints in order to single out this singularity. And each of these constraints will correspond to modulating out some symmetry of the singularity. So there's the speed at which the shock occurs, there's the time at which the shock occurs, there's the location of the shock, there's the direction of the shock, and there's the curvature of the shock. Now, to compare to the 1D case, you just have the speed of the shock, the location of the shock, so the time of the shock, and the location of the shock, and that would be 1 + 1 + 1 constraint. So you'd only have 3 symmetries you'd need to modulate away. But in the 3D case, you have 10 symmetries that you have to modulate away. And the direction of the shock is something completely new. But what's really difficult is the curvature of the shock. Okay, this is a symmetry that's very difficult that took us a while to figure out. Okay, so the aim is that we want to introduce, I have to move this again. How do we move? Yeah. The aim is to introduce 10 dynamic modulation functions that ensure that we zoom into a 3D Burger shock. And we'll use methods borrowed from ideas in dispersive PD with this modulated subsimilar analysis, which is pioneered by Mel, Raphael, Mel, and Zag. And there's a ton of references in this case, and I won't be able to go through them all. I will mention that these results have been used in fluids more recently. So there's sort of the work of Masmoudi, Gold, Kolo, Ibrahim on the Prandtl equation. Of course, there's Ilgindi's result on the incompressible 3D Euler equations. And there's remarkable new work by Mel, Raphael, Rodiansky, and Seftor on implosions for the compressible Euler equations, which is a completely different type of singularity than the singularities we discuss in this lecture, this seminar talk. So let me, I only have a few minutes, so let me briefly describe how I set these different constraints. So we have to shift and rotate the coordinates, and this corresponds to the location of the shock and the direction of the shock. We have to introduce some parameterization of the curvature, and as I said, this was a really difficult new thing that we had to deal with. That was incredibly difficult to figure out how to do it, but we finally did. So this deals with the curvature of the shock, and then we have to introduce, and so as a little, we got very frustrated with dealing with the curvature of the shock, and so the transform causes a sort of shear, and since I'm Australian and I got so frustrated, we named it sheep shear transform, and this sort of stuck as a sort of a silly joke in our paper. And yeah, so the point is, each time you do this transformation, you get these horrible equations that I'll show you that all is not lost in the end. We have to introduce Riemann invariance, and it's much more difficult in this case because you have to do it in terms of the direction of the shock and also the curvature of the shock. And I didn't say, you also have to scale in time and also subtract off. So there was sorry, I'm rushing this a little bit. You have to subtract off the speed of the shock, and you also have to rescale in time. So this is this rescaling in time, and that deals with all the symmetries. Okay, and so what do you get? You get these horrible equations. But the point is that if you just consider these blue parts here and this part here, then this becomes the 3D Burgers equation, and you want to show that everything else doesn't matter. Of course, one real difficulty in 3D is that you can't close everything in terms of the Riemann invariance and do everything in terms of L infinity spaces. You need to do energy estimates, so this is an additional difficulty to a 3D, but you can deal with them. I won't go into those details. And the other thing is that you have to take advantage of the geometric nature of the vorticity. And just to give a sort of toy model of the kind of arguments that you see in our paper, so I always thought this was a great general exam question. You take the Burgers equation, say, and you take a passive scalar equation, which is vectored by the solution of the Burgers equation, but you add this -3. Okay, and so in this example, they've added some extra terms, so you can have some interaction. But sorry, no, this is it. Okay, so you have the Burgers equation, and you have the passive scalar vectored by this and you have this extra 3 here. Now, what you might think is, okay, does the C1 norm of Z blow up? You might think it does because it's because of the C1 norm of the velocity vector vecting it does blow up, but it turns out that the derivative of Z does not blow up. And how you see this is you write things in terms of self-similar coordinates. So you assume that W is a generic blow up for Burgers. And what you get is that Z satisfies the self-similar equation, but you have this transport term which gets really large very quickly. And what it does is that if you flow along according to this transport, you see that if you start in any region here, then the trajectories will speed off to the left. If you start any initial data at any position here, you'll speed off to the right. And then the only position which will correspond to the trajectory that actually hits singularities will stay at e to the s on 2. So this seems like it's moving away from the origin, but that's only true in self-similar coordinates. In the original coordinates, you have to rescale by this by e to the 3s on 2, so it actually goes to 0. Now, if you plug all this in, you see that when you integrate sort of the integrating factor that you get from the equation for the derivative of Z, you can integrate it, and then you see that the derivative of Z does not blow up. So this is a kind of key estimate, and there's a lot of other ideas that go into play. And I will end very soon. One thing to keep in mind is that
Listen, there's a question by Sergey. Yeah. So Sergey, maybe you want to unmute yourself and ask the question?
Yeah, maybe I can do that later when Tristan is done.
Okay, very good. Fine, very good. So it's not urgent. Very good.
Okay, so one thing I want to emphasize is that all these techniques that we build up is a new way of looking at self-similar analysis. It's quite different than previous works. So previous works tends to work on sort of stability, spectral stability of the self-similar, of an exact self-similar solution or an approximate self-similar solution. This type of analysis is very much geared towards the transport nature of the equation. So an advantage of this is that we can really take advantage of all the geometric properties of this equation. It's why we can so easily deal with the vorticity, which has stretching, and we can also deal with entropy. It's because we can take full advantage of the geometry of equations, because we take a transport-like view of these equations. And in particular, so all the estimates are sort of done, or the majority of the estimates are done in Lagrangian coordinates in the self-similar regime, as opposed to energy estimates. And there's an additional part where you have to do a sort of Taylor series argument around the origin, but I just want to mention that this is a sort of a new type of self-similar analysis which is really adapted to fluid-like equations. And so there's difficulty in dealing with the so high-order Sobolev energy estimates, but this can be dealt with because the more derivatives you take in self-similar coordinates, the better the equation gets. You get sort of additional damping terms. And to deal with the vorticity and also to deal with the entropy, we really use that we have sort of pointwise Lagrangian trajectories, and we can have these pointwise bounds and split things up in terms of the geometric coordinates of the vorticity. Okay, and this is the result. It's a mess, but it's basically we know everything about the solution. It blows up. We know the regularity is C1/3. We can also prove that it converges asymptotically to a self-similar solution for 3D Burgers. We know that the vorticity remains bounded, and we just know everything. So I will leave it there. Or there's the last video of the shot, and I'll leave it there.